All right, I think that's our cue to begin. So thank you for coming, everyone. My name is Ethan Neal from University of Colorado Boulder, one of the organizers for the workshop on emergent phenomena of strongly interacting conformal field theories and beyond. It's a little bit of a mouthful, but I think the short version of that title, you can read it as emergent symmetry. So symmetry is one of the most powerful, ubiquitous ideas in physics. We all learn about in textbooks and in many of the physics classes that we take. Look through my copy of Peschke and Schroeder's field theory textbook, which is about 800 pages. Word symmetry appears on over 200 of those pages. It gives you some idea how important it is. Emergent symmetry and strong coupling is sort of the sort of ideas, the undercurrent of the workshop. In particular, to deal with strong coupling, we need experts not only in pen and paper calculations, but in numerical methods like lattice field theory. So the workshop sort of brings together numerical and analytical experts in both condensed matter and in high energy physics. And Aspen has really been fantastic to be here in Aspen. It's really just a great place for this kind of workshop where we just get together a diverse group of physicists and just talk to each other, learn from each other, try to connect. Okay, so that's a little bit of the background. Now my pleasure to introduce our speaker today is my colleague, Professor Anna Hasenfratz, also at the University of Colorado. So Anna got her PhD at Eötvös University in Hungary. She was a faculty member at Florida State and at the University of Arizona before settling in at Colorado. She's a fellow of the American Physical Society, and she is, I'd say, one of the world's experts in lattice calculations, in particular lattice calculations that are relevant for the kind of things we're discussing at this workshop: emergent symmetry, exotic field theory systems, renormalization methods, and all of those things. So without further ado, I'm going to turn it over to Anna to tell us about symmetry's exotic phases and masses.
Thank you, Ethan, and thank you everyone who showed up in this rainy afternoon. Indeed, our workshop, I am one of the organizers together with Ethan. I had a very long title, but I think it reflects really well of what we are trying to do. And even though, even though Ethan explained what the workshop is, my slides also contained an explanation, so I will go through them one more time. So emergent phenomena. At this point, I just think about it as something new, unexpected, that's not directly observable or obvious from the Lagrangian, like exotic phases, like the symmetric mass generation or SMG phase that we probably discussed over and over at every single session that or private conversations that we had here. Strongly interacting. That implies that analytical methods might provide guidance, like various Toft anomaly matching conditions, but we will need non-perturbative studies to really understand these systems, typically Monte Carlo simulations, either in Hamiltonian or Lagrangian formulations. Conformal field theories are everywhere these days. How they connect to what they are doing is that the phases we are interested in most often emerge from conformal systems. That's why we find them, and then we can ask that what are we going to do with those phases? And we don't always know, frequently we don't, but the idea is that they might help identifying beyond standard model theories in particle physics. They might help formulations of chiral gauge theories, and we don't know yet, but they are exciting and new and emerging. And finally, indeed, the interaction between the condensed matter and high energy community, and even within those communities, rather different approaches and directions have been amazing these last 2 weeks. I think that has been a great workshop, and I hope, if not convey what we have been doing, because that is really up and coming and still uncertain, maybe I can convey the idea or the general idea behind it. What's common? I already mentioned symmetric mass generation, which is very unusual and very new. So I want to start with something very basic, mass generation in general. How is mass generated? In classical physics, it is not. It is basically defined as the inertial mass or maybe even gravitational mass, but we don't ask where it is coming from. And in practice, it is stuff in an object, the number of protons or plus the number of neutrons. If you are a galaxy person, you will probably measure it in units of solar mass. It's still number of protons plus number of neutrons, at least to a good approximation. We need relativity to get deeper, where we can connect energy and mass. But we really need quantum field theory to fully exploit this direction, because in quantum field theory, we can see phenomena where energy and mass really turn into each other or interact, like in this Feynman diagram that I picked almost randomly, but typical. We see a particle-antiparticle creation, annihilation into a photon. Then we see the photon create a quark and an antiquark. We see one of the antiquarks emit a gluon, a strong interacting gauge boson. In principle, we could see bond state formations and so on. These are the kind of questions I would like to see, even though non-perturbatively. So as I am a high energy theorist, and the picture I drew came from the standard model, I want to spend a minute outlining what we know about the standard model. It's funny that this kind of pictures and posters about the standard model got so popular and well-known that every physics department I visited the poster, and most of the time very, very faded poster, a version of this picture. So indeed, we know most of the standard model particles pretty well. So what do we know? It's theory that combines the weak electromagnetic and strong interactions. The electromagnetic interactions describe any kind of charge interaction. The carrier is the photon sitting here in this diagram. It's a massless gauge boson. The weak interactions, the carriers are heavy, W minus, plus, minus, and Z bosons at the bottom here have typically 80 to 90 GeV masses. Understand where that mass comes from, one of the subject of the talk. And the matter particles are the leptons from tau, muon, electron, and the neutrino parts. So these are the weak interactions. And finally, the strong sector is described by an SU3 gauge theory. Again, the carriers are gauge bosons. They are gluons sitting right here in the right upper corner. The gluons are again massless. And the corresponding matter particles, the quarks, again, 6 of them are massive and they sit at the top of this diagram. So this really just shows the structure of the standard model. That the very center of it is the Higgs boson. So maybe that is the center of the universe, or at least the standard model universe. It is because, in some sense, because all the masses that you probably don't see in the slides, but in the second plot, there are mass values for each and every quark and the W and the Z as well. Those masses are generated by the Higgs mechanism. So I want to describe, because that is the first mechanism, the first example of how mass can be generated in quantum field theory. So let me go to that. Mass generation via Higgs mechanism occurs through spontaneous symmetry breaking. And it is such a general phenomenon that depending on what community you are coming from, it might be called Anderson phenomena or Anderson mechanism or Higgs mechanism, or any combination of the people who actually worked or developed the Higgs mechanism. But it is rather simple. What happens? We have a Higgs field that is just a scalar field. Different systems will have different scalar fields. The standard model has a two-component complex scalar field that I denote here by phi. And then there is a potential that describes the interaction of the Higgs fields. And the typical potential has a quadratic term, m squared omega phi in this case, and a quartic term, lambda times omega phi square. It doesn't really matter what the components or fields are, but we can just look at this potential. It's a quartic potential. We know how it looks. If the coefficient of the quadratic term, omega phi or phi square, is positive, it's just a parabolic potential, totally symmetric. It describes massive particles going up and down the wall of the potential. There is nothing interesting happening here. Symmetry breaking or Higgs mechanism happens when the coefficient of m squared turns to be negative. When it is negative, that this parabolic-like potential suddenly develops a valley. And because we have a field that has more than one component, in this case 4, but 2 would be enough, it is really a valley that is running around the bottom of the potential. So what does it mean? In this system, first of all, we have broken symmetry that can be characterized by the vacuum expectation value or the value of the field phi at the bottom of the valley. We call that web. In the standard model, it has a value of 247 GeV, but more importantly, it's related to that parameter m and square root of the quartic coupling lambda. Now, what else do we have here? There are particles or excitations that can go around the bottom of the valley. Those are massless. They don't require energy to go around. We call them Nambu-Goldstone bosons because Nambu and Goldstone were the first describing that phenomena. And if we have a two-component complex scalar that is 4 components, 3 of them will turn into Nambu-Goldstone bosons. So this system has 3 massless Nambu-Goldstone bosons. And then there is one more excitation that is basically going up and down the side of that potential. That is what we call the Higgs. If you look at the value of the Higgs, in this setup, basically just looking at the potential and calculating the curvature at the bottom of the valley, we see that the Higgs mass is square root of 2 times m. That is related to the mass parameter, its absolute value. Really, this is the picture of spontaneous symmetry breaking and the emergence of the Goldstone bosons. How does that turn into W and Z bosons and masses in the standard model? Well, we have to couple. If we couple the Higgs field, this phi to the 4 kind of interaction field, to the gauge fields of the standard model, that is the SU2 weak and the U1 electromagnetic field, some magic happens. It's not big magic, one can work it out probably in half a page of algebra, that the gauge bosons, the SU2 gauge bosons absorb the Goldstone bosons that showed up in the symmetry breaking. The Goldstone bosons basically become the longitudinal degree of freedom of the originally massless gauge bosons, and the gauge bosons acquire a mass. That mass is proportional. MW is the vacuum expectation value V times G2, which is the strength of the SU2 coupling. We can predict it if you know V and G2, we know the value, and experimentally, indeed, it has been identified. It's 80 GeV or so. The Z is a bit more complicated because of mixing between the neutral bosons, but it still can be predicted relatively easily. It has a value of 91 GeV. The first example of mass generation, again, through the spontaneous symmetry breaking and Higgs mechanism. What about the leptons and the quarks? Can couple those also to the field phi, the scalar field phi. And if the phi develops an expectation value, a Yukawa coupling which is the simplest and most standard coupling, will turn into an ordinary mass term. The fermions, mass of the fermion will be Yukawa coupling times V, the vacuum expectation value, and choosing Y accordingly to experimental values, we can reproduce all the values that have been observed for both the lepton masses and the quark masses. Really, this is what happens in the standard model electroweak sector. And you can ask that, what about the Higgs? It doesn't show up at this point. Really, the Higgs is only there to, it's a particle left to tell the tale. Does not directly enter into neither the gauge nor the fermion mass generation. The value of m of the 5 to the 4 potential does not enter in this section. It actually explains why it took 30 years to find the Higgs, because we could not even predict its mass. This is not a parameter that would come out like the other mass values. But the Higgs is there. We know by now that it has a value of about 126 GeV. It is indeed supports this symmetry breaking mechanism and mass generation. It's a beautiful construction. But if you count how many parameters there are, a lot. And all the masses, all the mixing angles, we could live with that, but it's not pretty. We would like to have something better than that. Another issue that people frequently quote when they want to find a beyond standard model system is that there's an enormous range of masses that the standard model describes, basically from zero, light neutrinos, all the way the top quark mass 173 GeV. Why is that? But nevertheless, I have to emphasize this is a very, very successful, maybe too successful, of a description of electroweak interactions. Unfortunately, it does not describe the world around us. It doesn't describe the solar mass galaxies or whatever. Why not? Well, it describes about 5% of it. Most of the mass in a proton, neutron, strongly interacting particles, like 95% of that mass comes from the strong force. So even though, especially when the Higgs was discovered, it was heralded as the God particle. It's a great particle, but it doesn't explain strong interactions and mass generation in strong interactions. So let's see why, or what's happening in the strong interaction. That is my second example of mass generation in particle physics. What do we have? So the strong interactions are described by the SU3 color force. There are 6 quarks, 3 of them are relatively light, 2 of them are really, really light, and then there are the gluons that are massless. That mix up all the hadrons, in particular the proton, contains 3 quarks, 2 up and 1 down. The quark masses are between 2 and 5 MeV. So the quark masses in a proton add up to about 10 MeV. Yet, the proton mass is about 2 orders of magnitude larger. Where does it come from? The same about the neutron. It contains 1 up, 2 down quarks. The total mass is about 10 MeV. The neutron mass is 2 orders of magnitude larger. This is the beauty or the interesting part of strong interactions. How does that happen? Why does that happen? I want to mention that I could totally forget about the quark masses. I could take them at least theoretically to 0, and I would get pretty much the same value for the hadrons. Really, the quark masses play very, very little role, at least in the spectrum of QCD. So let's move on to the strong interactions. We would like, or I would like eventually to discuss the spectrum and how the hadron masses are generated. But I want to start with something else first, because I will return that in a couple of slides. Because no colloquium could have some scary equations. I wrote down the Lagrangian for QCD. It contains the color gauge fields denoted by A and the quark fields denoted by psi. And don't worry about it. I am not going to do anything with it, at least not perhaps till the very, very end. The reason I wrote it down, because I want to point out the parameters. So what do we have here? There is a gauge coupling that shows up both in that G mu field strength tensor and also in the covariant derivative, which basically couples quarks to the gauge fields. So we have a gauge coupling. Frequently, instead of G, we use alpha. For alpha strong, it is just G squared over 4 pi. And then we have the quark masses Mi, one for each and every quark. Not too bad. If I take only the two lightest quarks for the proton and the neutron, then I have two quark masses and the gauge coupling. So that's all I have to describe here or consider here. QCD is strongly interacting and it has some very special properties. One of them, an unusual one, certainly when it was first discovered, it is that it's asymptotically free, meaning that at high energies or very short distances, this gauge coupling alpha goes to 0. That is, within a proton, the quarks barely interact. They are at very short distance. There is asymptotic freedom. On the other hand, if I go to very large distances or high energies, the opposite happens. The coupling goes to infinity. And that is not a theory. This is actually measured experimentally. I have here on the right a plot of the coupling alpha as the function of the energy. So again, the main point here is that whatever we call strong coupling is not a number, it's a function of the energy where we measure the interaction. And we see that it shoots up quite significantly as we go down to lower energies. It is just the opposite of what you would see in QED in electrodynamics, that the coupling is weak at large distances and strong at short distances. So this is the coupling of QCD. Now let's see, what do we know about the spectrum? There is a whole book of hadrons that have been identified, all their properties, spin, parity, whatever, probably well over 100 of them. They are all built up from quarks. We put them into basically two categories. Mesons are quark anti-quark pairs. Baryons have 3 quarks. And then recently, like in the last decade or so, experimentalists identified more exotic objects like pentaquarks or 4-quark objects. I am going to concentrate, of course, on the, not of course, but I will, on the simple lightest states. So here is an example that's an experimental plot. It shows the lightest mesons. That is, mesons that are basically made up, I think all of them made from up and down quarks, really the light mesons. Here is the pion, the lightest particle. It's about 140 MeV. Then the rho meson, which is again the next most common, is 770. There are vector particles at 1200, scalar at about 1000. We again see that separation that we have perhaps seen before when we talked about container symmetry breaking, that we have one relatively light object, particle, the pion, and everybody else is heavy. This suggests maybe the mass generation in QCD is again proceeds through spontaneous symmetry breaking, just like in the Higgs, basically Higgs mechanism, and we expect the pion to be the corresponding Goldstone boson. Indeed, that will happen. We understand it quite well, how and why. If we have a QCD-like system, SU3 with certain number of flavors, if I have NF number of fermions, quarks, that system, the Lagrangian, has an SU-NF cross SU-NF left-right symmetry, basically left-handed and right-handed quarks, and pick up a phase factor independently. But that symmetry breaks down spontaneously to SU-NF, basically vector-like symmetry, and that spontaneous breakdown is very similar to what we have seen in the Higgs mechanism. Namely, it has a vacuum expectation value that in this case turns out to be the fermion condensate, psi bar psi. It has a value of 270 MeV around. The pions are indeed the Nambu Goldstone bosons of this symmetry breaking, and the Higgs, if you wonder, is there a Higgs field in there? That would be the sigma particle around 500 MeV. But all the other particles are there. They are generated by different Dirac and flavor indices. Of course, the pion is not massless. The description I had before, about when I talked about spontaneous symmetry breaking, there was a valley that had no energy required for the particles to move around. That's not the same for the pion, but it's very easy to modify the system, physically tilt potential. Like an external magnetic field, lift one hand. Yes?
Does it matter that that's a global symmetry that breaks? It's not a gauge symmetry. Does that matter?
Oh, absolutely. We don't. So good. I don't break gauge symmetry. And you might be thinking of that, yeah, the Higgs mechanism breaks the gauge symmetry of SU2, but that's not the same. That was broken. What was broken spontaneously was the Higgs potential. And then when coupled to the gauge field, it broke the electroweak symmetry. These symmetries are all Roberts symmetries.
That's why the stone remains massless.
Yeah, absolutely. So this is the setup that explains basically hand-wavingly of what happens in QCD. And then I'm sorry. I am good. Sorry, I got distracted with the question. Good. So this explains what we see experimentally. The question that is that QCD Lagrangian that I bored you the previous slide, is that indeed the theory of strong interactions? Does that describe what we see experimentally? So the question is QCD the theory of strong interactions? Does it show confinement? Does it reproduce asymptotic freedom and the running coupling of alpha measured? And does it reproduce the experimental hadron spectrum? Great questions that are very difficult to answer for two reasons. One, alpha S is strong. That's why they are strong interactions. And then even more important problem or issue is that when we take our QCD Lagrangian, we can derive analytically how massive objects like hadron masses depend on the gauge coupling G, that coupling or parameter that I showed before. And that derivation shows that at lowest order, the mass of a hadron will be proportional in a functional form to exponential minus 1 over 2 beta B0 G square. B0 is just a number. It's important here that we have a form, an analytic form, e to the minus 1 over G square. Now we know that that is not analytic at G square 0. So there is no way we could do a perturbative expansion and get any information about the hadron spectrum. This is a strictly non-perturbative problem that probably is best solved, certainly today and maybe in the foreseeable future, by doing some kind of computational simulation like Lattice QCD. I had a slide about Lattice QCD, but I thought that there is no way I can discuss more about LQCD than just that it exists. So what is Lattice QCD? We take that QCD Lagrangian, we discretize it, we turn it basically into a statistical StatMax system, which is great because then I can think about the Ising model that I learned back in undergraduate years and develop an intuition. So I take this statistical system, put it on a computer, do Monte Carlo simulations, calculate whatever I want. Of course, there are a lot of LQCD practitioners in the audience, and they should shake their hand because it is much, much harder than that. But for now, just take my word for it, we can do it. I'll do that also for a living. So this is an example of what comes out from a Lattice QCD calculation. These are the light mesons, and this plot actually shows baryons, like here is the nucleon, here is the lambda. It also shows some heavy mesons and baryons, but don't worry about that. Just look at the bottom here. What you should see, I know it is a small picture, but what you should see are black lines that are the experimentally measured values for certain hadrons like the pion or the rho or the kaon. And then the colored symbols are Lattice QCD calculations, and those numbers come from different collaborations, different methods, different formalism, and they pretty much all agree. I think this is an absolute success story of Lattice QCD, that we can do that. And I try to find a really up-to-date spectrum picture like that. This is almost 10 years old. Didn't. And I think the reason I didn't find any, because we are so certain that we can do it, that we don't publish spectrum anymore. It's done. It was done 10 years ago. Lattice QCD people moved on to more exciting things like calculating hadronic contribution to G-2 or heavy flavors, other things. But I think this is a beautiful example of how it works and why we believe QCD describes strong interactions and why we believe that we can handle QCD in numerical simulations.
Just out of curiosity, there's only one line here which is missing a dot. You know what's up with that? That's like around 1200 MeV.
There is probably no prediction. That's a heavy, and actually it's not 1200, but there is a gap here where they subtracted like 4 GeV from the values. So forget this up here.
Oh, okay.
But if you have a very sharp eye, you might see that some, like the pion, doesn't have a line. And some other places the line is missing. Those are the inputs. I was kind of swept that under the rug. We can't predict everything because we have the parameters. We have to fix somewhere the value of the quark masses. We also have to fix the value of the lattice spacing or the gauge coupling, but that can be done through the gluonic sector. But if you look at it, there are values missing here that are the inputs. The issue is that these are 4 different calculations, and groups tend to use different inputs. They choose a different quantity. The input, so that I could not just say M-pi certainly sets the up and down fermion mass. The kaon typically sets the strange quark, but not always, and you can go on. So this there is a bit of trickery in here. This is actually all I wanted to say about the spectrum and mass generation in QCD. I would like to move on to something in the next 10 minutes or so that is something that I've been working on in the last couple of years, and I think it is very connected to what we have been doing here in this workshop. So let me go back to that running coupling, the plot that I already showed before, alpha or g squared over 4 pi versus the energy scale mu. It's a perfectly good running coupling, but if you look at it analytically, it has all sorts of logs and inverses. It's not a very pleasant form. It turns out that it is much better to take its derivative. That is, take the running coupling, take its derivative with respect to the energy scale and multiply it by mu squared. So it's a dimensionless quantity. We call it the beta function or renormalization group beta function because indeed it comes through renormalization group. And this is the quantity that we prefer to characterize the running coupling or the system. So if I take the QCD running coupling and turn it into a beta function through this formula, I will find that it starts at 0, it is all negative, going to increasingly larger values. The beta function is a good quantity because it does have a perturbative expansion. It's not a mass quantity. In fact, we know the perturbative expansion to 5 orders, but the first 2 will do. Thus, those values are universal, they are negative. This is the region that describes asymptotic freedom, that is small coupling. And then as we go to stronger couplings, higher energies, beta function has an increasing slope, that is the confining regime. So can we reproduce that on the lattice? Before I show that we can, I want to mention that it's not just show that we can do lattice calculations. This non-perturbative beta function is essential for several phenomenological or lattice calculations. We use it to predict alpha S at the Z boson scale. And also this quantity can signal or identify phase transitions in more complicated systems. So this is a very generic or important quantity. So here is an example. Strangely, lattice methods only very recently got to the level that they can predict the beta function from very weak coupling to very strong coupling. I think that probably is, first of all, there were theoretical progress that led to a new method that I will refer to as continuous beta function or CBF. And probably it took 20 or 30 years to develop it because people were more interested in the spectrum than in the beta function. But now we know how to calculate the beta function, and here's an example. This is the analog of what I showed as a sketch before. We have a perturbative regime agrees perfectly well with perturbation theory. And then if you go to larger, stronger couplings, and this is really strong coupling, it's already in the confining regime, what you might see that this beta function is actually looks linear. It doesn't look like a higher order polynomial. One can actually go there, fit it, it looks linear. This is very consistent, the fact that this system is confining with a linear force between quarks and n-type quarks. Now, to be fair, this example that I am showing here doesn't have any quarks. We have done that with my student, Curtis Peterson, an undergraduate, and Oliver Witzel, who is sitting in the audience, in the pure Yang-Mills system that is no fermions, but there are calculations ongoing with 2 flavors and 3 flavors. So we know how to do that, but this is the only one, I believe, with this method that is actually published. So that's why I'm showing it. Thank you. And I am also proud of my student Curtis because he did most of the analysis and he did a great job. I also want to mention that using the beta function, we can calculate something called the QCD lambda parameter. That's for people in the audience who know QCD. Our prediction is that red point here. There are two more predictions here using the similar or same approach, but different calculations, different actions, whatever. And there is quite a significant tension between the new values and the old values as they are listed in the particle data group. I think this is something we'll have to understand. I believe that it is the old calculations that had issues, but it might have a significant effect on high precision calculations. Then says I have 10 minutes, 2 minutes ago, so I will speed up, but I want to show something new, non-QCD. I want to take this beta function and change the number of flavors, add more and more and more quarks. I wrote down here the perturbative expansion of the beta function, and if you see it from a distance, you see that the fermion number NF goes against the pure gauge value, so it can change the sign of the beta function coefficients, and indeed that's exactly what it does. So if I take the beta function, again, these are sketches with small number of fermion numbers, like less than 8. We had the QCD like beta function or negative, the system is confining, chirally broken. But then I increase the number of fermions to above 8, maybe 10, 12, and suddenly the beta function develops as 0. That is interesting because that's different physics. In fact, if this is a confining system, chirally broken system, this beta function implies a conformal symmetry. So we move simply by adding more fermions. These are massless fermions. We go to conformal. And then if we increase the number of fermions even further, we even lose asymptotic freedom. This is a beautiful sequence. And what could be even more beautiful is we really don't know how the beta function develops at 0. So when I drew this one, this is the simplest version. The beta function goes to 0. We don't know what else happens. We know the phases exist. We don't know where it occurs, and we don't know exactly how it occurs, but there are good indications, theoretical hypotheses, that the conformal phase actually will show up not just linearly going through 0, but through developing a bump in the beta function. And if that happens, we have very, very interesting systems. Namely, it could be that the beta function has a bump, but doesn't quite reach 0. In that case, we still have QCD, but this is a very strange QCD, what we call walking. These are the systems that are frequently suggested as BSM, beyond standard model theories. Just have to find the flavor number or see if that actually happens. This is even more interesting when the beta function touches 0, because we have a conformal system, we have a fixed point or a phase transition, and whatever happens in the strong coupling side, we don't know, but it is not QCD. It is not QCD and it is not conformal. I would put this as the first sign of an exotic phase where we really don't quite understand the system behaves. Certainly perturbation theory is not helping us. And then increasing the number of flavors even further, we have a clean conformal phase and again, an exotic phase there. So these are the questions that I am mostly interested in. And these are the questions, at least partially, that we investigated in this workshop in the last 2 weeks. And maybe in the next 2 minutes, I just show some examples that we can do that. We still don't quite understand. We don't understand everything, but we have made baby steps to see what is happening. And this is an example from a lattice simulation. Here, I'm using 10 flavors with SU3 gauge, measuring numerically that beta function that I described. And all I want you to see is that beta function has a 0 here. That system numerically, and it took a while to actually get to it, but by now we have very strong evidence that this system with 10 flavors is conformal. So we have to go below 10 flavor if we want to find working behavior or the edge of the conformal window. I'm going to skip that, but I mentioned that if 10 is conformal, then let's try 8. We could try 9, but 9 is hard. So let's just do the easy part. Let's do 8. In 8 flavor, numerical simulations suggest that we actually have a continuous phase transition. And because I am out of time, I am not going to explain what exactly you see here. I am just saying that it's a continuous phase transition from a conformal phase. So I am quite certain that the beta function is either the left or the right, not QCD-like. And then we can ask that, can we decide actually which one it is? Numerical finite size scaling analysis suggests that that flavor number is actually the seal of the conformal window has a beta function that just touches. You should say that why on Earth? Why 8? Why not 7.8 or 8.2? And I don't know. But we can ask that, is there anything special about 8 flavors? And the answer, I believe, is yes. And that was, again, part of the discussion that we had in the last 2 weeks. 8 flavor with these fermions have a very special property. Basically, we call it Toft anomaly cancellation, and don't worry about it, what it exactly means. It is a special property that happens only at 8 flavor or multiple of 8. And that ensures that this system could be fully gapped. It could break, or it could describe mass generation without breaking chiral symmetry. And indeed, that seems to be happening. This continuous phase transition that so far we have seen only numerically suggests that there is a phase, the strong coupling phase, that is confining, chirally symmetric, has no Goldstone bosons, has no spontaneous symmetry breaking, yet fermions are massive. So this is my last statement in here. This is the example that is not standard. We have not seen that before. And I am not claiming that this is well established. This is really part of what we have been thinking of or trying to do in the last 2 weeks in this workshop. And I think we'll keep on doing that, and we'll try to understand if really this is the direction we can go. Also, even if we find it theoretically that this phase exists, we don't yet have an explanation or indication that nature realizes this phase. Nevertheless, it is very exciting that it might exist. And really, that's all I wanted to tell you today. I am just leaving you with a couple of parting thoughts as a conclusion. So mass generation in quantum field theory is a very important and valid question. In most systems, both in high energy and condensed matter, it proceeds via spontaneous symmetry breaking. However, recent developments, and it really started from condensed matter, and I apologize for my condensed matter colleagues not describing that tremendous development that they and others understood in the last 6, 7, 8 years or so. Recent developments suggest that spontaneous symmetry breaking is not the only possible mechanism. If it is indeed the case, then we could have new kind of phases, both on the lattice and in continuum quantum field theory. These new phases could describe very new phenomena, very new different mass generations, but almost certainly they are strongly coupled. So I and my lattice colleagues are standing here ready to understand them and see what we can do with them. So with that, I stop. Thank you very much for your attention.
Questions?
I just want to know what's a good intuitive way of thinking about this particular mechanism.
Well, we don't have SSB. That's a great question, and you should have sat through some of our sessions. That's exactly the question. One idea, and I'm not sure if that is the way to go, but one idea that seems to have might work is that what happens. So first of all, we know that what we need is a new interaction that connects 4 fermions instead of only 2. That can be done with a Yukawa coupling, but not just with any kind of Yukawa coupling, but very specific kind of couplings. And when we get rid of the Yukawa coupling or the scalar field, that leads to 4 fermion interactions. So it is generally believed that we need 4 fermion interaction to drive this symmetric mass generation. And it is quite possible that the 4 fermion, that a 4 fermion interaction term or a 4 fermion term will eventually condense. And that is when the symmetric mass generation occurs. But again, I am saying the words, in condensed matter, this has been established. In 4-dimension high energy physics, where I am coming from, we are still at the very early stages. We are really just following what we learned from lower dimensional systems.
I notice you never mentioned dimensional transmutation, a la Coleman and Weinberg. Do you just see that as covered by spontaneous symmetry breaking then, or?
No, I don't think it is the same. You have dimensional transmutation without fermions as well. I kind of implied it, but I was running too fast when I said that we cannot calculate the Hadron masses because we have an explicit analytical form of how they behave. That is dimensional transmutation. That's where it is coming from. That is, I think the question, if you have never heard it, means that we have a Lagrangian and the gauge coupling is dimensionless. If I ignore the fermion masses because they are not relevant at that level, then how on earth will that Lagrangian describe anything massive? So there is a magic happening there, which is called dimensional transmutation, that leads to that expression. And also when I run through this lambda parameter, that's again dimensional transmutation. I don't think that has anything to do with chiral symmetry breaking. This is within the gauge sector.
Can you comment a little bit more? What do you think is the reason?
Okay, so Marina asked that why is there a tension between the new calculations for the lambda parameter and the old one? The old ones use different methods, but the problem is that the lambda parameter really needs the beta function. That's the definition. And if you don't have a well-defined scheme that connects very weak coupling, like G square of 1, to strong coupling regime where there are dimensional transmutation and confinement, like G square of 15, then you really don't know what's happening. And the new method, this continuous beta function method, I believe is the only one that does that in a given fixed scheme without relying on perturbation theory or any other kind of magic. But this is my hunch. I know what we did here to get this point. I more or less know what the others did here, but it's the same method. So I think it is up to the community to go and understand what happened with the older calculations, which you see are 10, at least 5 years old. So those are older calculations. I think it's important, and you know that it's important for kind of work you are doing. Mm-hmm. Okay, I don't know.
Go ahead.
Okay, just quickly, what is 3-loop GF and why does it go up?
Good question. This is the beta function is scheme dependent. On the lattice, we calculate it in a scheme which is a gradient flow scheme. Doesn't matter if don't know what it is. It's a scheme. In that scheme, one can do perturbation theory. And Robert Harlander and people around him did a 3-loop calculation for the beta function and found this blow up thing. Nobody knows why. 3-loop gradient flow seems to be very, very poorly behaved, non-convergent. I think that's an interesting question. Sometimes I think it could be some kind of tadpole or whatever, but we don't know. It's a perturbative calculation. If you look at it, it looks perfectly fine up to about g squared 5, and then it just loses convergence. Okay.
Could you please comment on your most favorable mechanism for confinement that you've learned from the lab? I mean, mechanisms that actually create these spring tensions between quarks and antiquarks. What are the insights from
Confinement. I'm not sure. I don't know. So confinement certainly comes out here. It is a linear behavior. There have been papers claiming that this confinement is coming from. I have the feeling it is due to instantons. I would understand it via instantons, but I am not going to bet my house or other things on it.
Yeah. And maybe 2 questions for that are interrelated. There are some studies in QCD which use continuum methods to maybe identify these beta functions, say non-perturbative, such as functional renormalization or Schwinger-Dyson equations, which evaluate perturbative endpoint functions in these settings, but in the continuum method to get this discretization. Have people made an effort trying to compare these non-perturbative beta functions? Because apparently this contain the information for these systems. That's question 1. And related to that, you highlighted that confinement relates really to the divergence of the gauge coupling in the infrared limit. Can you explain that a bit further? Because I was under the impression that that is very independent. Some people claim that actually gauge coupling reach finite values.
To answer your second question, absolutely. I mean, I agree with you. This is very scheme dependent. In that specific scheme, we found a very linear beta function. And I have my doubts that it will be like that in other schemes. I know that people, let me not refer to papers, try to explain, for example, the strong CP problem by claiming that the beta function is linear. I don't know if I really trust it. So I agree with you. It is, it's citing. It's not a proof or more than a citing. And then for the beta function in different schemes like functional renormalization, it's a great suggestion. We have not compared it. Maybe there you would not see the linear dependence, but I know what I would need to compare to make sure that the FRG is actually capturing. FRG has approximations. And to really show that it captures the physics, it would have to reproduce the lambda parameter. It would be very interesting to take an FRG scheme, beta function, integrate it to get the lambda parameter, connected it to MS bar. This is all MS bar here. I can tell you what the square root of 80 is, just a dimensionful number. We could compare. And I would love to see it. I think that that is a great idea to go that direction.
Well, we're exactly at the hour, so I think let's thank Anna again.
Thank you.